Hi, this is Mrs. Clark, and today we are going to talk about how we're going to round, how many numbers are going to keep when we do a math problem in our calculators, and talk about the significance of the figures or numbers that we use. So let's go ahead and get started. When we talk about doing a problem, you always get a lot of numbers in your calculator, and you always wonder how many you're going to keep. Well, there are really specific rules, and they're kind of based on what numbers you put into your calculator in the first place. So there's two kinds of numbers you could have put in, either an exact number or a measured number. An exact number is not a number that could even be rounded because it doesn't have an extended amount of figures following the number. So if I have an orange, I have one orange exactly. There's not 1.0000 oranges because I couldn't round that any which way. And so that's what I'm talking about with an exact number. However, if I want to measure the weight of that orange, I could record that to a lot of digits. And so that's a measured number. And so those are the two different types of numbers we'll talk about today. So an exact number is obtained when you count objects. Like I was saying, one orange is 1.0 forever oranges. So I don't need to specify my accuracy when I count something like soccer balls or pizzas. Also, exact relationships. When we talk about the relationships we have with numbers, a lot of times when we are converting, we'll use the number 1 for one of our conversions. And that is a definition, and so we don't need to have that limit the significance of our answer. So a foot equals 12 inches, and those are exact relationships. Let's go ahead and do a learning check. So question A. How do we obtain exact numbers? Go ahead and take a look at those options. And question B, how do we obtain measured numbers? All right, if you said exact numbers are obtained either by counting or definition, you're right. And you should also know that measured numbers are obtained by using a measuring tool. This could be a ruler, a balance, a thermometer, any tool that has measurement. Even if it stops measuring and only has 2 digits after the decimal, if we had a more accurate way to measure that, we could record more numbers. Go ahead and take a moment to classify each of these as either exact or measured. So pause, identify, and I'll be back. Welcome back. All right, so 1 yard equals 3 feet. This is a definition, and so it is an exact number. Diameters are measured, and so it is not exact. 6 hats on the shelf is an exact counting number, and gold melts at 1064 degrees Celsius is a measured number. All right, so when we do measure something, we always have a degree of uncertainty. There's a point where our measurement can no longer be extended by another digit because we run out of accurate markings on our measuring device. So when we look at a graduated cylinder like this, we can zoom in and look closely to find out where the water ends in our measurement system. Here we definitely know that the first number will be a 1 because it's between 15 and 20. So that means it's between 10 and 20. There's no guessing going on there. When we look at the next digit, we also know that this is 15, this is 16, this is 17, this is 18. So we know that the number is between 17 and 18. Those are certain digits. There's no question whether or not the first digits are 1 and 7. So we've got 17 here. That's no question. Now, there's one final digit that we have to guess about. And a best guess is always needed for that last digit in any measurement. And so when we're talking about a balance, it does that guessing for you, or a thermometer will do that guessing for you. But when you're looking at something that has measured numbers, when this number is 17 and this number is 18, you have to guess what goes in between. You're always going to measure at the bottom of the meniscus. And here the guess is 7. So we could say that it is 17.7 milliliters. Would it be correct to say 17.6 or even 17.5? Sure, because the last number is estimated. You will not be held accountable to have that come out exactly the same way as your neighbor would. So go ahead and write down what you think the length is of this black line. So we can see the marking is between 1.6 and 1.7, so we'll need to guess one more digit beyond that, which means that if I'm guessing, I might guess 1.67 as my measurement. What if you guessed 1.66? Is that still okay? Absolutely. What is the length of the wooden stick? Go ahead, pause, and take a guess. Welcome back. Is it A, 4.5 centimeters, B, 4.54 centimeters, or C, 4.547 centimeters? Well, the key is that you can only guess one digit. I know it's 4.5, I don't have to guess that, but it's that 5.4 that I have to guess. This would have two guessed digits, so this cannot be the answer. So the answer might be 4.54 centimeters. One more, go ahead and tell me how many centimeters long this pencil is. Let's talk about the length of this pencil. Now we know that this is right around 8. Now how accurate though is it? Is it 8.0? Is there a marking for 8.0? Yeah, because there's 8.0, 8.1, 8.2. Since that means our 8.0 is certain, we need one more uncertain digit, making this 8.00. A ruler like this would be measured to 2 digits after the decimal. So, do you see why measured numbers have error? We have to guess the last digit, and any time that we're responsible for something, that means there's some inherent error. We definitely have to record all the digits we know with certainty, and then have one more digit at the end that we have guessed. Take a look at these two numbers and think about what is the difference in the meaning of these two numbers. Really, the difference lies in the amount of precision in the number. The first number is only measured to 2 digits after the decimal. The second number is measured to 5 digits after the decimal. This means a much more precise measuring tool has been used, and so we know a lot more information about the measurement itself. Alright, so now we know how to measure an object, but in order to calculate using that measurement, we need to be able to identify the number of those figures that are significant. Sometimes we get this out of a measurement, sometimes we get this as a given in a math problem. So let's go ahead and look at the rules, the 3 rules that determine how many digits are significant in a given figure. The first rule says that zeros at the beginning are never significant. So if we look at a number that starts with zeros, we know that we can get rid of them because they're not significant. With or without a decimal, it doesn't matter. Rule 2, captive zeros are always significant. That's a zero in between 2 non-zero numbers, or in between a non-zero number and a decimal if the decimal comes later. Zeros at the end of a number and after a decimal point are always significant. It's assumed that these zeros would not be shown unless they were significant. And so if you see this number right here, these numbers tell us, just like in that last slide that we talked about, that there is a large amount of precision and accuracy involved in the measurement of this number, giving us 3 digits after the decimal. This is a very specifically measured value, and so therefore it has 6 significant figures. When we talk about the dot, that means the decimal. So if there's a decimal, the zeros at the end are significant. If there's no decimal, the zeros at the end are not significant. Go ahead and take a look at these and figure out how many digits are significant in each problem. Go ahead and pause and come back. Alright, welcome back. In the first problem, all of the digits are significant because there are no zeros, and so we're guaranteed they're all significant figures. In the second problem, these zeros are before, and remember, the beginning zeros are never significant. This leaves us with 3 significant figures. In the next problem, we once again have leading zeros, so they are not significant. The 239 is of course significant. Now, because these zeros are both after significant figures and after a decimal, they are significant. So that leaves us with 5 significant figures. The next problem has a decimal at the end, and this is a special exception kind of case where these are being held captive by that decimal, making them significant. In the next problem, there is no decimal, meaning that they're not significant, leading with two significant figures. This is like the difference between saying Eastlake High School has 3,000 students and today, this morning, one more student enrolled in our high school, and now we are at a capacity of 3,000 students. We have to be able to tell the difference scientifically when we are rounding or when we are being exact, and that decimal helps us to do that. The following number has 4 significant figures. The times 10 to the portion does not count for significant figures. Finally, the next one, all digits count. We have captive zeros, and we have an end zero beyond a decimal. When we do math, the rules are going to change, and so the question is, how do you decide how many digits to keep? There are some simple rules that are going to help you determine that, and it depends on what kind of math you are doing. Let's start out by talking about rounding. You should know if a number is 4 or less, it's going to just drop off and not affect our answer. For instance, if I'm taking this to 2 significant figures, this 2 is below 4, and therefore I round to 2.4. If the digit to be removed is 5 or greater, we are going to round up. Or sometimes I'll say, it's time for a round up. All right, in this case, the 8 is higher than 5, which means that it is going to round the 5 up to a 6. If there are a few steps, it's best to round off at the end. So don't round to your least significant figure until the final answer that you're going to report. This means that rounding will contribute less to your error. Go ahead and try to round all of these into 3 significant figures. Welcome back. The first one to 3 significant figures would be 1.56. The second, 0.0374. Remember, these are not significant because they are beginning zeros. 1367. Now we have to round up, and the only way to do that is to call it 1370. When you look at a problem like this, I want you to think, all right, is this closer to 1360 or 1370? And then write the answer. 128,522, again, is this closer to 128,000 or 129,000? 129 is the correct answer. And finally, 1.6683 times 10 to the 6th can be rounded to 1.67 times 10 to the 6th. All right, go ahead and try to turn these into a 4 Sig Fig number. Pause. Welcome back. To round the first one to 4 significant figures, we're rounding a 0, and so we don't need to keep or round anything. In the second case, we're rounding an 8, but since that 8 is beyond the decimal, we need to know, is this closer to 780,500 or 780,600? And that is obviously closer to 780,600. 1999.5 can be rounded to 2,000, but in order to make 2,000 be significant to 4 digits, we need to add a decimal. Now let's take a look at the math. When multiplying or dividing, what we're limited by is the least amount of sig figs we put into the calculation. So no matter how many things you multiply and divide, we need to look through every single number, determine its significant figures, and then round our answer to the least of those significant figures. So in this case, we have 3 and 4, and that means our final answer must have only 3. When we add, we look at the dad. That is a crazy saying, but that is my saying. When we add, we look at the digits after the decimal. And so here we have 2 digits after the decimal. We have 1, 2, 3, 4, 5 digits after the decimal. In the end, we can only keep 2 digits after the decimal because the first value had only 2 digits after the decimal. If you are talking about a number that is rounded above the decimal and its less significant figure occurs earlier, you have to round all digits to that place. So we'll look at an example in just a moment. Go ahead and look at all of these and figure out how many digits you should keep in each situation. Because these are all multiplying and dividing, you're going to want to round to the least amount of significant figures given in the problem. Go ahead and pause. Welcome back. The first one should be limited to 3 significant figures because this has 3 significant figures. Second problem, 3 significant figures, 4 sig figs, we have to round to 3. In this problem, we have 4 significant figures versus 1, 2, 3, 4, 5, 6 sig figs, which means we're limited to 4 significant figures. Here we have 1, 2, 3, 4, 5 sig figs versus 4 sig figs, so we can keep only 4 sig figs. And finally, here we have 4 sig figs and we have 4 sig figs. So even though we have lots and lots of zeros here, we can cut it off to make 4 significant figures. Addition and subtraction. Go ahead and pause, work out the 3 problems that are on your handout, and then we'll go over them. Welcome back. The first problem, we have 1 digit after the decimal and 3 digits after the decimal. Because when you add, you look at the dad standing for digits after decimal, we are going to have to cut it off right here because there is 1 digit after the decimal. And that will give us an answer of 59.8 because this 7 will round up that 7. Here we have 2 digits after the decimal, and here we have 4. That means we're limited to 2 digits after the decimal, giving us an answer of 32.72. Finally, here, this is a different kind of problem. Where is our last significant figure here? 1 digit after the decimal. Here, it's 1 digit before the decimal, right? And that means our entire answer will have to be rounded to the tens place, giving us an answer of 330. So what we always want to do is look for that last important digit, or what I like to call the digit after the decimal, or dad. When you add, look at the dad. 2 dads or 3 dads, we're going to round to 2 dads. Go ahead and pause and work out the remaining problems. Welcome back. Let's go over the answers. 82,000, 0.1, and 0. Why is the last answer 0? So is this closer to 10 or is this closer to 0? This is closer to 0 than 10, meaning that the answer that you record would be 0. It's unlikely there will be a lot of questions that are that severe on your tests. Go ahead and try out these mixed order of operations. Remember PEMDAS as you work them out. Pause and give it a go. All right, we take a look at this problem, and first we've done the multiplication because of PEMDAS. And once we have all of our multiplication done, which limited us to 4 sig figs between these 2 problems, now I have 2 dads, 2 dads, and 1 dad. This 1 dad will limit our final answer to 239.6. Let's try the second problem. Here we're going to have to add first because they're in parentheses. Now when we multiply, I have 4 sig figs and 4 sig figs. So what can I keep? 4 significant figures. Because it came out to a nice even 80, we have to put the decimal there because that indicates that this 0 is significant. All right, hopefully you got enough out of the lesson today. We'll practice this in class. Thanks so much. Have a great night.